Welcome everyone to this lecture on beginning scientific computing, where we're going to talk about our logic structures for programming a diversity of codes. In fact, almost everything we're going to be doing in this course is going to be based around two sets of logics: if statements, for loops. And in fact, all of scientific computing really starts to revolve around these two central themes. As we put them together, we can build quite incredible codes for use in a variety of engineering and physics-based problems. So the website is here. So if you look down here, you can follow along there. You can go to this link. It has not only additional course materials, but also has the codes that I will go over today in this lecture, as well as notes and a variety of other materials. So you can find that link in the description of this video. So logic, everything is going to be based around programming logic for ourselves, and so we want to start developing some infrastructure for starting to understand how all of this works. So the first thing to think about is we'll start off with the if statement. The if statement broadly is something like this as a construct. What it is a very simple if statement that says if, and then there's some kind of logical statement here. So it could be something simple like if x is bigger than 3. And if it is, if that satisfies this logic, it executes some expressions, right? So the idea here with this if statement is to ask or interrogate the data that you're working with or the computations you're working with. And if something is true about that data, do this. You can also say else if something else is true about that data, do something else. Else if something else is true about the data, and then if none of that's true, you just say else, do this here, and end. Okay? So the idea has a beginning and an end, and it has a series of logical questions. So it could be something like, if x is between 1 and 2, do this. If x is between 2 and 3, do this. If x is between 3 and 4, do this. And if none of those are satisfied, you would do something like this. If I don't have the else in here, then it could go through this whole thing, none of it's satisfied, and nothing is done. So this is a very generic structure of how to frame an if statement. You get to decide what should be asked and what should be done as a consequence of meeting that logical expression. Okay, so that's it. The if statements are pretty simple logic blocks that we're going to start building around in our code. Same thing here, you can just do it even as small as this. If this is true, do this. Else if, another expression, do this, and then end. Again, it either has to satisfy this or this to even do anything. Okay? If none of those are satisfied, it just walks through this if block and does nothing. And that's okay too. You may just want to start asking and interrogating the data and asking certain things about it, and if none of them are satisfied, you just keep moving on with computations. So that's the basic structure of the if. And what we're going to do in just a little bit here is we're going to actually show how to use if statements and building some little coding blocks for ourselves. So that's the if. There's not much else to be said about it, except we'll demonstrate it in practice as we come through this. The partner to if is the for loop. The for loop is this concept of basically going through a loop a certain number of times and iterating through a loop. So for instance, in Python or MATLAB, a for loop can look just like these two right here. So on the top, you have the Python code. And in that Python code, again, we're going to come in and we're going to bring in NumPy as NP. So we're going to do some computations. So you want to bring in NumPy. And then notice this code block here. We're going to start off with a equals 0. And we're going to do in this loop is for j in range 0, 5. So what this is going to do in the range is going to go start from 0, and since I haven't specified a step, it's just going to start stepping forward 0, 1, 2, 3, and 4. Remember, it does not step at 5. It does one less than 5. So it's going to go 0 through 4 in integer steps. And what does this loop do? It says a is equal to what it was before. Remember, it came in as 0, plus j plus 1. Since I started counting at 0, comes in as 0, I add 1 to it, so 0 plus 1 is 1. A was 1, or 0 when it came in, so it's 1 plus 0, it's now 1, that value. Okay? And I can display that value here. And then the next time through the loop, now j is 1. So if j is 1, this is going to be 1 plus 1 is 2. Remember my previous value of a was 1, so it's 2 plus 1 is 3, and so forth. So you're just walking through this loop and just adding numbers to itself. But that's it. So this is the most important part of the loop, right here. Tell it some variable and tell it to walk through that variable a certain number of times. MATLAB is similar, and here, notice the difference between Python and MATLAB. In Python, the indentation matters a great deal. So when you do a for loop, when you're in this indented space, it means you're in that for loop. Okay? There's no end statement to it. MATLAB puts an end to it. So wherever there's a for, there has to be an end. And there's this convenient little graphical display here if you're often doing MATLAB, which is this, okay, the for begins here, the end begins here, especially as you start going to bigger level code where we have a lot of for loops. This is a very handy way to keep track of when does a for loop start, when does it end. In Python, it's all indentation based, okay? So in MATLAB, for j, again, same thing. Give it a variable and tell it to walk through this variable from 1 to 5. And since I haven't specified a step, it's going to go from 1 to 5 in steps of 1. It's going to be 1, 2, 3, 4, 5. Okay? So this is going through the loop 5 times, and so is this. Except I started counting here at 0, and it goes to 4. This starts counting at 1 and goes to 5. Same thing here. Just update the value of a by adding j to it. So this is a very simple structure. I just made it do this operation in the beginning, but really this is the important line of code right there. Tell me how to walk through the loop. So that's what we're doing with the for loop. You can walk through this loop in a lot of different ways. Just like we created vectors and matrices, you can say for j in range, go from 0 to 5 in steps of 2. So I can go 0, 2, 4. Okay? Here, same thing, go from 1 to 5 in steps of 2. So 1, 3, 5. Remember, the code structure is interesting. Python, beginning, end, step. MATLAB, beginning, step, end. They're just slightly different, but they function the same way. And so it's important that you just recognize that difference. And again, in the for loop, there's no end to it, it's just indented. And in MATLAB, there's a for and an end. Okay, so those are very basic structures. And here's a little bit more robust way to represent the data, which is I can go through this loop, 1, 5, 4, 1, 5, 4. So I'm going to make a vector. And what I want to do is loop through these values of 1, 5, 4. So for j, it goes in loop. So what this is going to do when j is in the loop, it's going to actually step through. First, the value is going to be 1, then 5, then 4. And that's what I'm doing in here. So it's not going to be just incrementally through a loop. I have to always step it in steps of 1, 2, 3, 4. Notice what I'm doing here is just step through the values of a vector. Same thing here for MATLAB. For j equals 1, 5, 4. It's a vector. So it's going to first go through the first component of the vector, second component, and then the third component. So both these code structures are really flexible in how you decide to execute a for loop. Okay? So you always get to prescribe what you want to do in that for loop, what do you want to walk through, and that's going to be one of the really most important coding blocks that we're going to use throughout this course in actually solving many of the engineering and science problems that we have throughout in our time in doing this course. Okay, so what I thought I'd do is show you how for loops and if statements work together. We're going to do a simple example of a root finding exercise. So what I'm showing you here is there's some function f of x, and here it is, right? You can see it here. It's this orange curve. And what I'd really like to find is the following. Find the value of x where this thing is 0. So this is a very simple thing that we often do in the sciences is root finding exercises. So that's the point I want to find. I want to figure out what's the numerical value of this point. So what I'm going to do is use a combination of for loops and if statements to do this. Okay? So that's going to be the exercise. I'm going to write a code to do this. So here's how we're going to do it actually. So first of all, we have to have some kind of algorithmic way to do this. Remember that this course is really focused in all on the algorithms that we're going to sort of bring to the table to solve a lot of varieties of problems. And we're going to get pretty sophisticated at the end, but this is just the really beginning portions of building the baseline or the groundwork for what we do and to do more sophisticated things. But even the more sophisticated things we do are based strictly on for loops, if statements, okay? So here's something that we might have. We might find that, like, okay, I have this curve, and this point here, x of r, this is the right point, its value of f of x is positive. For x of L, it's down here, and so this is negative. So somewhere between x of L and x of r, right? So somewhere between here on the left and over here on the right, I went through 0. Suppose I know that. So one very simple way to sort of zoom in and find this 0 crossing point is to use what's called bisection. Okay, so I'm going to illustrate this concept, and then we're going to write a code for it in what we do. So we know, first of all, that it's somewhere in this interval. So this is what this magenta line is trying to depict for us, is somewhere between the left and somewhere between the right. I have crossed 0, and I'm trying to find that point where I crossed 0. So what bisection does is simply says, how about if I go halfway in between them? Pick a point between x of L and x of r. So you can just find the midpoint between those 2 points. This is called xc, so the center point. And you ask the question, what is the value of xc? Oh look, the value of xc is still negative. So since I know it's negative here and it's positive here, I know then it has to cross somewhere in this region. So this is what this green region is meant to denote. So I started off knowing that the point was in this magenta somewhere. And by taking one cut across this with a bisection, I know now it's over in that region over there. Okay? So that's the concept of bisection. You keep cutting things in half. So I cut it in half. I zoomed in on the location a little bit. In fact, I went from it being twice as big to half as big in terms of the location where I think this thing is. And then I just do bisection again. Cut that in half. So if I cut this in half between where the green and the magenta line is, I know it's in here. So now I go right to the midpoint. Here's the new midpoint. And look, I'm positive. So if this is positive here, negative here, I know it's in between here. So this is denoting that now I've shrunk down the interval to where I know the solution is to be in this region here. So bisection progressively squeezes in to the location of this point, which is right here. Okay? And I could just continue iterating this over and over again, keep cutting it in half and in half and in half and in half again. So this is what we want to do. We want to write a code that automates this process for finding the root of this problem. Okay, so before we start coding, let's talk about just even that pictorial of what we did and count the number count how we're going to have to actually build code for this. So first of all, when we think about this bisection method, there's 2 things we're going to have to do. What I always like to do ahead of time is count how many for loops and if statements do we need. Okay, and before you start programming, figure out what those numbers are. So first of all, let's talk about how many for loops. The for loop that we're going to have here, it's one for loop because I'm going to go progressively through and just keep cutting the interval in half. That was my bisection. I started off, I cut it in half, I cut it in half again, I cut it in half again, I cut it in half again. And so my for loop might say, I'm going to just cut it in half 1,000 times and see if I can get to the solution. Okay? That would be a for loop. Now notice, every time we cut it though, we always had to ask the question, is the midpoint above or below the line, right? Is it positive or negative? And that makes all the difference in terms of where do I make the next cut. So right away, there's an if statement. The if statement said, if it's positive, do one thing. If it's negative, do another thing. Okay? And finally, we have yet one more if statement, which is once I get close enough to this point, I should stop. It's not clear I can land exactly on the 0, right? It could be some complicated number with lots of decimal point places. You might want the solution, let's say, with 6 decimal place accuracy or 4 decimal place accuracy. And once you get that solution to that accuracy, you should stop. Okay? So there's one for loop, and in that for loop, there's 2 if statements. One, to ask the question, am I above, if I'm positive or negative, and if I am, do something. So that's where our logic piece will come in. And one is, if I'm close enough to the solution, stop. So that's what we're going to be working on in trying to write a code to do this in an automated way. Okay, so here's going to be a very specific example we do. Here's a plot, and so what this plot is of this function here, f of x equals e to the x minus tan x. Okay, so if I look at that function, here's what it looks like. And by the way, these lines here are just simply because we have asymptotes due to the tangent. So it's going to negative infinity here, positive infinity here, and then of course plotting wise it makes this jump. But this is where I really want to look at is these zero crossings, which is here, here, there's one over here, there's one over here. So in fact there's quite a few zero crossings. In fact, if you go to the negative direction, right, so this side of things, then you'll get an infinite number of crossings, and this is partly just due to the fact that you have a tangent. Okay, that always, right, multiple crossings of 0 with a tangent periodically. So what I want to do is I want to actually focus in on this crossing right here. I want the value of that point where this crosses. So that's what we're going to do. We're going to figure that out. Okay, so what kind of information am I going to have? I obviously plotted this plot, right? And I could just keep zooming in on that. But really what I'd like to do is have an automated way to just give me a number to prescribe precision of where that crossing is. And so we're going to use the bisection to get this. So the first thing is to understand that's the point we're after. And maybe what I really want is to get this point down to like 10 to the minus 5 or 6 accuracy. Something like this. That's all I want is 5, 6 decimal place accuracy. Okay? The other thing I have information on is the point negative 4 is right over here somewhere, so it's positive, and negative 2.8, it's over here, it's negative. So I know that, roughly speaking, it's somewhere between negative 4 and 2.8. And if I'm in the negative 4 regime, right, over here, I'm positive, and if I'm over here at negative 2.8, I'm, in fact, negative. Okay? So I want to bisect this in order to squeeze in on it, knowing that my left point is positive, my right point is negative, and then I'm going to cut it in half, determine if I'm a positive or negative, cut it in half, keep going through that process that we just drew in the bisection to converge to this solution. So let's talk about some code that would do this. So what I've done here is actually giving you code side by side of MATLAB and Python. And so I want to walk through these codes because they basically have everything we need to go ahead and execute this bisection and come up with our solution. So first of all, both codes start off with something simple. The right point is negative 2.8. The left point is negative 4. Okay? The right point, negative 2.8, I know that in fact the values are negative there, and the left point, negative 4, the values are positive. So at first just define these 2 points where I have information on the values of the function there being positive and negative. Same thing up here with MATLAB. That's my right point. This is my left point. Okay? So I know my zero crossing is between those two values. So now what I'm going to do, remember, I have to have one for loop, which is going to walk me through cutting this thing, the bisection, and then 2 if statements in between it, okay? So here we go. In Python, for j equals in range 0, 100. So it's going to say walk through this thing from 0 all the way to 99. So it's going to be in this loop, and it's going to be in there 100 times, unless the if statement pulls me out of it, okay? So that's the idea. Here is my loop. Notice the for statement. Everything here is indented. Everything here lives in this for loop. Okay? Here's MATLAB for j equals 1 to 1,000. And I did 1,000 here instead of 100, but you'll see in a minute it's actually going to converge pretty quickly, and we're never going to go through this loop 1,000 times or even 100 times. What we're doing is just saying, here's a loop, do this loop up to 1,000 times. The first thing we did, remember, is we said find the midpoint. call this x of c. So here's the midpoint. X of c is the average between the left and right points. That's it. So you take the 2 points divided by 2. Same thing with MATLAB. Take the 2 points divided by 2. Then, once you have the midpoint, you evaluate the function. Here's the function at that point. np dot exponent, np dot tangent, minus np dot tangent. So by the way, you need the np here. Remember, this is numpy entered in as np. So anytime you access functions like sines, cosines, exponents, tangents, you say np exp or np tan. You can't just say exp or tan, okay? You have to say np because it's calling on that package where those functions are defined. MATLAB, you don't need to do that. You just say, here's e to the x minus tan x. And then you're done, okay? Now the first thing we do is now we started off with these 2 points, the left and right points. We found the middle point, and we just asked the question, is it positive or negative? Remember, when we did this, right, for the left point, it was positive. For the right point, it was negative. So what we're going to ask is, if in this midpoint I'm greater than 0, that means I'm still above the line. That means what I can do is my left point now becomes the center point. In other words, I can move that left point over to be the new center. The new left point is this center point I just computed. Because I know at this point the value of the root is on the right of the interval. So that's what you're just going to ask. Is this function positive or negative? If it's positive, do this. Else, the right point becomes x of c. In other words, this is either true, in which case it's positive, that means it's still on the right. But if it isn't true, that means it's actually the other way, which is it's on the other side of the interval, which means the right point now is updated to be x of c. It's exactly like this picture I drew for you here, okay? Let's come back to here. So this is your updating continuously the left and right points. So when we initially started with these 2 points here in the magenta, first thing we did, cut it in half, and we got the green point. And we noticed that this is still negative here and negative here. That means it's over on this interval here. So this is now the left point. Okay, so the new left point is this value of xc. Then I cut it in half again. Notice that this point here is positive, so I have positive here, negative here. That means this here is now the right point. So I can take this new value of x of r as this point here. So notice what I'm really doing here is I keep updating the left and right points as I cut this down just with these if statements. And that's exactly what we've done here, is we've updated either the right or left point depending upon where it sits in the interval. So you do it here with MATLAB. Notice the if statement, there's a colon, and then an else colon. That's the structure of an if. And in MATLAB, if fc is greater than 0, this, else this, end. Now, one other thing I want to point out here is you'll notice a lot that I have a lot of semicolons around in the MATLAB code. So what semicolons do is suppress output to the screen. So it's interesting, Python and MATLAB have taken 2 alternative views of what goes to the screen. So MATLAB, unless you put the semicolon, every computation you do will get pushed out to the console, so you'll see the values of these computations. So if you do a lot of computations, you'll see all this stuff popping to your console. And a lot of times it's just annoying. So you can put a semicolon and it suppresses the screen output. Python does it the opposite. Python never pushes things out to the console or to the screen unless you say it and you say something like this, display. So you have to explicitly tell it to plot to the screen or else it won't do so. Okay? So that's your first if statement. So you came into this for loop, you start your bisection, and when you're doing the bisection, you're starting to basically ask the question, cut it in half, shrink your interval, and the if statement helps you to shrink it in the correct way. But what this second if statement does, it's separate than the first one, just simply says, if the absolute value of f of c, remember f of c is what I'm trying to make 0. I'm trying to find when is this function 0. So if this function is less than, let's say, 10 minus 5, then I'm done. So I'm going to display the value of x, display j, which is the number of iterations it took. Remember, j is up here. And then break. What break does is it kicks you out of this for loop. Okay, so once that piece of logic is satisfied and you have a break statement, it gets you out of this loop. Just like here it does in MATLAB. If absolute value is less than 10 times 5, show me the values, break. And this break statement takes you out of that for loop. Okay? So that's a really nice piece of logic. So you don't necessarily want to stay in this for loop 1,000 times or even this one 100 times. In fact, you get convergence to the solution with this tolerance in only 13 iterations. So 13 times through the loop, it just keeps cutting it in half 13 times, and now it satisfies this criteria you've specified here, and you're done with the computation. And this ensures that you finish the computation. The break statement just says, get out of this loop. There's no need for you to do 100 iterations or here 1,000 iterations because you've actually already computed the value of the root. So this is a nice little code, and I'd say if you can study this code and do this example, it's really quite illustrative of the kind of programming structure we're going to be using throughout this course, right? We're trying to solve something practical, which is find the roots of a function. That's something we often do in science and engineering, and you can see it's a pretty simple structure. Again, I always emphasize, make sure before you start writing code to start thinking about the overall architecture. And the overall architecture here, it was one for loop, and embedded in that for loop I have to have two if statements. A lot of that you can think about ahead of time, and once you have that in mind, you can come into programming this and be a little bit more efficient in terms of your results. And by the way, remember, this thing converges in 13 iterations. You can just run this code, either one, MATLAB or Python, and that will get you these results very nicely. So these are the kind of codes we're going to write throughout the course. And there's nothing really that fancy here, but most codes aren't actually that fancy. Everything's built on these very simple structures of if and for loops. And with those, we will build amazing code bases for doing lots of very practical things for solving problems. So just keep that in mind. If and for, those are our programming blocks. It's not going to get any fancier than that, really. And we're just going to build all kinds of things with it. Again, go to the website. You can download the code and find more links to the notes and video lectures here. And also, the link is right in the description of the course page.